Alright, so I wanted to make a short video trying to describe how to solve this particular force on an inclined plane. And see, we said in the problem that the plane was frictionless, right? And what other special things did we know? No friction, and mass was m, near the surface of the Earth. I think I said that this force was F naught. I forget if I gave numbers or not. I'm sorry guys, I left the statement of quiz 2 at school, and so I'm just going off memory at the moment. But I think I'm going to capture the main features here that you're probably interested in. And I will then, of course, try to post a complete solution for you guys once I get my hands back on the quiz. So, Hannah, I'm recording a video right now, girl. So, the basic problem here is that to find the sum of the forces on the mass, we have to come to terms with the fact that we still have the gravitational force, right? So we could illustrate the force of gravity. If I wanted to, I could draw it as if it was acting right here, just for the sake of convenience on my picture. And so, gravity acts down like this, right? So if you look at it like that, of course that's mg, right? And there's two pieces to that. There is the piece which goes along the plane, parallel to the plane, right? This piece. I can't even see it. This piece, right? This piece of gravity, and then of course there's also the perpendicular piece of gravity, which I'll make blue here in a moment, right? So these two vector components to gravity give us the part of gravity which is parallel and the part of gravity which is perpendicular and to the plane. And if you look, right, you can see that this angle here is also theta, right? So we have this part, the blue part, is mg cosine theta, and the purple part is mg sine theta. Now we talked about this before. This is not new. All right. What's new? And then of course we also had the normal force, right? Which of course is normal. And so let's make this picture properly ugly. It would go normal to the plane, something like this. My picture's starting to get really busy, isn't it? Not to scale or anything, just that's the normal force, right? Which I've called Fn. So we've got a normal force, we've got a gravity force. I took gravity, I put it into the parallel component and the perpendicular component, right? And then the same is true of the pushing force, this external force F naught, right? I've got to rip that apart also into its parallel and perpendicular components, because remember, vector force is a vector, and to understand it we have to take the vector and rip it apart into its constituent directions in such a way that we can add them. And so choosing a pair of perpendicular directions is just a good idea. Now, so I made the parallel component of F naught brown, and I will make the perpendicular or normal component to F naught. I'm going to make it orange. All right, so there is the perpendicular component to the force. There's the parallel component to the force, right? Let me call this F perp. Let me call this. I'll continue with my silly color coding. F perpendicular, and parallel rather. And I would point out that the geometry here informs us that this angle is theta again, right? So you've got F naught is the length of this little right triangle, and so we can see from that triangle then that the parallel piece is given by F naught cosine theta, and the perpendicular piece, I am now a slave to my color coding, F perpendicular is F naught sine theta. Yeah, you can play with Bennett. It's fine. Welcome, Isaac. There's the Isaac you guys met today. And let's see here. All right, so at this point, I'm going to, just make another picture just to organize my thinking, if you don't mind. All right, so here's my plane. Right, here's my box. And I'm just going to draw the forces I was just drawing a second ago here as if they're at the center of mass, because that's the the custom for a free body diagram. So here's the proper free body diagram down here, right? Very exciting. Here's the normal force. All right. Then we have, and so what I'm going to do is rather than write the gravity, I'm going to write gravity as if it's two forces, right? Because it's really two forces as far as I'm concerned. It's this parallel part, the parallel component of gravity, mg sine theta, like so. And there is also the perpendicular part of gravity, like over here, mg cosine theta, right? And let's see, so I got those two guys make the gravity, we've got the normal force, and now we got to take care of our parallel and perpendicular components to the pushing force F naught. So the parallel component is, oh man, what was that? No, Legos, whatever. The parallel component, F parallel, I have made brown as well. And that goes like so, right? So that would be F, let's see, well we had a specific formula for it. It's F naught cosine theta, the parallel part of it. And the other part, the perpendicular part of the pushing force, it's pushing down. It actually gives the kind of an apparent gravity in some sense, right? It kind of gives the appearance that the box is heavier than it actually is because you're pushing down on it as it's pictured, right? So that is F perp, which is F naught sine theta. I think that's everything at play here because I believe I said it was frictionless, so I think that's all she wrote. I mean, that's the sum of the forces that are on this box, and so we can now take account and sum the forces in the parallel and perpendicular direction. And of course, I don't know. I can't tell you who's the winner without knowing how big F naught is as it relates to mg, or even what the angle is. Without knowing the specific angle and the specific F naught, I can't really say much more. But I can choose a system of coordinates and write down Newton's laws, whether or not my acceleration is positive. It doesn't mean that I can't write these laws down, so let's do that. And so let's see here. I'm gonna say gravity wins just for kicks, and so I'm gonna say down is positive. With down is positive, in other words, sliding down, we have ma, and that's the parallel a, right? Equals to what is the sum of the forces along parallel direction. Parallel direction, we've got mg sine theta pointing down, and we've got minus F naught cosine theta going up. All right, that's Newton's second law in the parallel direction with what's at play. In the perpendicular direction, we have 0 because we're assuming the box stays on the plane. The perpendicular acceleration 0. And that means that the force's perpendicular sense must balance out. So we'll take up as positive, so we got the normal force, like so. And then minus F naught sine theta minus mg cosine theta. All right. Now, so that would be it, and then we can go and try to answer whatever question I asked. I don't unfortunately remember what question I asked, But that's the setup, and you can use whatever's given to solve for whatever you want there. So now that I've done this much, and I've gone this far, let's throw friction in the mix. What if, in addition, we threw in friction? How would that change anything, if anything? So let's add friction. And let's add kinetic friction. Let's assume this thing is moving. All right. Add kinetic friction. Assume the box is moving. Then we have a force of friction is mu sub k times the normal force. That acts which way? And then the question is, it's moving. We need to say which direction it's moving, right? So I said we're going to assume gravity wins. Let's assume it's moving downwards for the sake of... If it was moving upwards, then we'd have to do this slightly differently, right? All right. If it's moving downward, then I can picture the force of friction. What's it go? It's going opposite the motion, right? So the force of friction would get added to the free body diagram like here, right? And all that would change is the parallel direction would have minus mu sub k, right, times the normal force. We'd slow down the acceleration according to that friction term. So that's pretty much it. Now, if it were going, if the motion happened to be, if you had given the box a shove up the plane, instead of a minus there, I'd put a plus, because the the friction force would be going opposite of the motion, which would be down in that contingent case. So that's how you do this kind of problem. The same principles as before. We just take the extra force and break it into its parallel and perpendicular components and figure that into our Newton's laws. So I hope this helps you guys, and I will try to write a complete solution to your quiz hopefully tomorrow. Unfortunately, like I said, I just didn't bring your quiz home somehow in the excitement of packing up my office with the kids. I left your quiz sitting on my desk and not in my backpack, and unfortunately my memory is not photographic, so I do not remember what I put on the first page of your quiz, unfortunately. So anyway, again, hope this helps, and have a good night. Thanks.